Okay. Good morning, everyone. My name is Akira Nordmeyer, and I'll be talking to you guys about continuous flow bioreactors for production of biofuels. I'm going to be talking primarily about the importance of biofuels, what a bioreactor is, the types of bioreactors such as batch and continuous, and current research, both that is being done and my current research, and why this comic makes complete sense. So first off, biofuel, it's fuel that is derived from biomass or made from biomass. And it's important because transportation industry relies heavily on our fuels, and biomass is the main resource that is easily derived to fuels as a substitute for petroleum fuels. So here's some counterparts of biofuels to petroleum fuels. We have, of course, biodiesel fuels to replace petroleum diesel. We also have bioethanol and biomethane for gasoline. We have biogas and biokerosene for kerosene. Today I'll be mostly talking about bioethanol and a little bit of biomethanol. So first off, ethanol. Ethanol is the most commonly used in biofuel additive to gasoline. Right now, the gas you buy at a gas station is about 10% ethanol. And this is because production of ethanol has tripled in the past few years. In 2000 to 2007, we went from 17 billion to 52 billion liters of ethanol production. In 2011, that was 84.6 billion liters produced. And it is projected to increase even further. The reason for this is it's easily produced. We can use yeast or bacteria to produce ethanol. As we're all familiar with beer formation of beer, wine, or even spirits. Another key thing for ethanol is its energy potential. It is 1.5 gallons of ethanol is equivalent to about a gallon of gasoline. And you can see how much ethanol is consumed by Americans every year. Methanol is not so readily used as a biofuel, mainly because of its low energy potential. It's 2 gallons of methanol for every gallon of gasoline, which makes it not very feasible. But it is primarily used in the formation of formaldehyde, acetic acid, as well as biodiesel. It also is used in waste management facilities to remove nitrogen for denitrification. And the main reason for removal of nitrogen in waste management facilities is because nitrogen can't be released in large quantities into the environment. Otherwise, we have proliferation of algae or of other bacteria. And so it has to be removed from waste streams. So a bioreactor is a vessel in which a chemical process is carried out through the use of an organism. Ethanol is formed through glycolysis, which is a process that breaks down sugar. Theoretically, you can get about 2 moles of ethanol for every mole of glucose, or 4 moles of ethanol for every mole of sucrose. Sucrose is commonly used as table sugar, and right now many bioreactors are used in beet production plants or even sugar production plants for waste management facilities, where they are able to produce bioethanol from that. So, batch reactors. A batch reactor has large yield, but it's one time. It is slow and time consuming, on average of about a month and a half to 2 months. They're expensive to produce and maintain. It requires large area. The smallest batch reactor is about 1 liter, and they go up to about 15,000 liters. It also requires heating and cooling, depending on where you are located in the world. Most of the batch reactors that are currently in production or in use are in Brazil for sugar and beet production. And during the summers, they have to cool their systems to make sure that it maintains at about 28 to 29 degrees Celsius. It also has to be cleaned after every use. And after it's been cleaned, the bacteria has to be reintroduced into the batch reactor and allowed to grow before any substrate is placed into the batch reactor. It also requires constant stirring. So this batch reactor makes it very inefficient because we spend a lot of energy in order to obtain our ethanol production, not even to separate it out. You need to distill it still to get your ethanol. So not the most efficient way of producing our ethanol. A continuous flow reactor, it would give a smaller but yet continuous yield. They are smaller in both area and volume. They are ideally inexpensive to produce, maintain, and to operate. The only thing you need is a heating or cooling system in order to keep your bacteria at the optimal temperature, which is 28 to 29 degrees Celsius. And the greatest thing about the continuous flow reactor is that you can integrate it into your pipeline as is. It doesn't require large areas, and it doesn't have to sit for long periods of time. Now, the current research that is being done, the cell immobilization in bead reactors is the ideal standard right now for continuous flow reactors. The efficiency is about 68% efficient, and there's some papers that boast a 72% efficiency in ethanol production. Traditionally, yeast or bacteria are immobilized in calcium adjuvant beads. These beads are semi-permeable. The reactor is a simple and compact design, as you'll see in the next slide. These are the beads that are here. They are formed through a mixture of the bacteria or yeast in a sodium adjuvant and dipped into calcium chloride solution, which allows it to harden. But this reactor is not without its faults. There are many problems. The beads itself, they expand in size, which slows flow rate. The reactor has to have excess area so that the beads can be allowed to expand in size. This lowers the efficiency over time, and it's not stable. These are also considered semi-batch because the beads themselves absorb some of the liquid before releasing them into the solution. So we want to produce a continuous flow bioreactor that is actually continuous, where it does not absorb some of the solution and then release it over time, which will help to increase our stability and our efficiency. We want to build a reactor that is simple in design and use, easier to maintain, cheaper, and hopefully allow for larger flow rates. So we believe that a cell immobilized mesh polymer is the best way to go. A mesh polymer will be insoluble in water, which means that the morphology won't change, allowing for size changes, as well as it will help to stabilize ethanol production. It will increase our surface area to the bacteria or yeast. As you can see here, this is a fiber that has our encapsulated bacteria, Xybomonas. The process, the polymer is synthesized using a very common F127 polymer. We remove some of the methyl groups and add different groups and double bonds into the polymer. Once the polymer has been synthesized, it is able to be dissolved in water. We mix it with polyethylene oxide, or PEO. This helps in the next process called electrospinning. Electrospinning helps us to obtain nano-sized fibers, and this is what the mesh will look like, or fiber mesh will look like before, while they're still soluble in water. The electrospinning process, there are many different factors that change your size of your strands. The main factors are your viscosity of your liquid, your flow rate, your distance, and electrical potential. A syringe tip has an electrode applied to it that produces a positive potential. A collection plate is then grounded, and the fibers are pulled out of the syringe at a reasonable flow rate. We have optimized at various conditions. As you can see, there's many different things that can change it. So we primarily use 18 kilovolts as our electric potential, a distance of 4 inches, and a flow rate of approximately 0.1 milliliters per minute. After electrospinning, the fibers are still considered soluble in water, so we have to go through what's called cross-linking to remove PO as well as some of the methyl groups, so to make it insoluble. This is what the mesh looks like after cross-linking. This mesh has to be placed into glycerol until use, mainly to keep the bacteria alive and healthy. Our future work, we have to perfect the cross-linking technique. Our fibers, our mesh is still a little soluble in water. And then once that is done, we have to optimize it, because the cross-linking solution is actually very detrimental to the bacteria and yeast. So we have to try to eliminate some of the chemicals in the cross-linking solution or lower the concentration in order to allow our bacteria to survive the cross-linking step. Then we must design a reactor and test our mesh to see our efficiency, and redesign to improve our efficiency as well. Any questions?
How long it does it take for bacteria eat 1 mole of sugar?
In most of the continuous cell reactors, the traditional flow rate is about 1 ml per minute, and that allows for about 50 to 60% efficiency depending on the reactor. The bead reactors that I showed, they're optimized at about 1.8 mL per minute, which when you think of the overall scheme, that is very slow, but these are meant for tabletop apparatuses, and they should be able to be scaled up relatively easily, and the flow rate should be able to be increased.
How long would the bacteria live inside of your polymers if you had them already in there and you were flowing through the reactor cell?
They should, depending on what solution they're being fed, if they're in a beet production plant or a sugar production plant, they should be able to last 3 to 6 months. If they're to be used in waste management facilities, they're probably not going to be able to get as much nutrients as they need, and would probably need to be replaced about every 3 to 4 weeks.
Why do you use glycerol?
Glycerol is very easy for the bacteria that I'm using to break down, and it offers them all the nutrients that they would need, and so it keeps them healthy and they're happy. They're happy.
Thank you.